Okay, here we go with the topic computing with scientific notation. Let's go ahead and get started. Number one, which shows the expression below in simplified form. So, what is that expression we're dealing with? We're dealing with two things that are written in scientific notation. We have 7 times 10 to the sixth multiplied by 6 times 10 to the negative third. Let's break this down so you can see exactly what we're dealing with. We are dealing with four things we're multiplying together. We've got the 7 right there, multiplied by 10 to the sixth, and we're multiplying that by 6, which is being multiplied by 10 to the negative third. So it's just four things we're multiplying together. And you should know that multiplication is commutative, which means it doesn't matter the order that you're multiplying everything in. You're just multiplying the four things together. So I'm going to show you a shortcut for how to do this, but first I'll explain it the long way so that you know what you're doing when you use the shortcut. Here's the long way. You don't have to do this every time. This is just me explaining why the shortcut works, and I'll show you the shortcut at the end. First, I'm going to write out this whole thing, but without parentheses, because I don't need parentheses if it's nothing but multiplication. Here we go. I've got 7 times, and I'll just use a multiplication dot for times, 10 to the sixth power times 6 times 10 to the negative third power. Now, if I reorder that, if I put that in a different order, which I'm allowed to do because it's just four things I'm multiplying together, and the order that you multiply things doesn't matter, I could put the 10 and the 6 in a different order. I could start, or 10 to the negative sixth power and the 6 in a different order. Let me start with the 7 that we already have. And now I'm going to say times 6. And then I'll say times my 10 to the sixth power. And then I'll say times 10 to the negative third power. Now, I apologize if this looks like the negative sixth power. It's not to the negative sixth power. It's just my writing utensil isn't working that great. It's a positive 6 right there. So we have 7 times 6 times 10 to the sixth times 10 to the negative third. So hopefully you know 7 times 6 is simply 42. So 7 times 6 is 42. Then what is 10 to the sixth times 10 to the negative third power? We just did the first part, and I'm going to go over here. I'm going to change colors so we can see this a little bit more easily. 7 times 6 is 42. But what is 10 to the sixth times 10 to the negative third? We did a lesson earlier where if you are multiplying two things with the same base but different exponents, you add the exponents and keep the base. Our base is 10, so we're going to keep the base 10. And we're going to add the exponents 6 and negative 3. 6 plus negative 3 is just the same as 6 minus 3. So we have just 3, so 10 to the third. So what we have is 42 times 10 to the third. And that's the answer, but you notice that isn't written anywhere here. And the reason is because 42 times 10 to the third, while that's the right mathematical value, it's not in scientific notation. You need to remember that the requirements for scientific notation are that the leading number before the times 10 part has to be between 10 and 1, has to be less than 10 and greater than or equal to 1. Well, this number is 42. That's clearly way more than 10. So I have to change this so that it is less than 10 to start with and more than positive 1, or greater than or equal to positive 1. The way I'm going to do that is I'm simply going to take the decimal point that you can't see. It's an invisible decimal point. Let me change my color again so we can see that. I've got green now. If I take my invisible decimal point, which is right here, I thought I changed it to green. Let me try that one more time. So the invisible decimal point is right there. It's 42.0. If I move that over one spot, I get 4.2. So I'm changing my 42 into 4.2. But I don't want it to be 4.2. 42 was the right value. Making it into 42 or 4.2 makes it 10 times smaller. When you move a decimal point, you're either making the number 10 times smaller or 10 times bigger. So if I change 42 to 4.2, I just made it 10 times smaller. Well, since 42 times 10 to the third was the right value, in order to compensate for making 42 10 times smaller, I need to multiply by something that's 10 times bigger. So I'll change 10 to the third into 10 to the fourth. So 42 times 10 to the third is the same amount as 4.2 times 10 to the fourth. The 42 part becomes 10 times smaller to make 4.2, and the 10 to the third part becomes 10 times bigger because it's 10 to the fourth. In the 10 to the third part, you're multiplying by 10 3 times, but 10 to the fourth, you're multiplying by 10 4 times. So clearly it's 10 times bigger, and that balances out with the beginning number, the leading number, which is 10 times smaller. So we have 4.2 times 10 to the fourth as our answer. So what is the shortcut? You don't have to write this all out every single time. You just have to remember these two steps. The first step is multiply the leading numbers together. 7 times 6, you get 42. Then multiply the times 10 with the exponent parts together. So this is times 10 to the sixth, and this is times 10 to the negative third. When you do that, it should always be a 10 if you're using scientific notation. So all you have to do is multiply the two numbers, and you could do that by adding the exponents. 6 plus negative 3 is just 3. So add the exponents and keep the 10, and you'll have the second part. So 7 times 6 is 42. And then 6 plus negative 3 is 6 minus 3. So we say the exponent is 3. And we keep the 10 exponent. Then after that, you just have to make sure it's in scientific notation. If you have a number that's more than 10, you have to make your number 10 times smaller. And when you make it 10 times smaller, you add 1 to the exponent on the 10 in order to make that part of the expression 10 times bigger, so that you are keeping your values equal. So 4.2 times 10 to the fourth. Let's try some more problems here. We have 4.2 times 10 to the fourth. Let's go ahead and do some more of these. Number 2, the radius of Mercury is approximately 2 times 10 to the third kilometers, and the radius of Uranus is approximately 2 times 10 to the fourth kilometers. To determine approximately how many times bigger the radius of Uranus is than the radius of Mercury, Ken performs the following operation. So we have 2 times 10 to the fourth minus 2 times 10 to the third. So approximately how many kilometers bigger is the radius of Uranus than the radius of Mercury? So we're just subtracting here. So how do we subtract? Well, there's a rule. When you have bases and exponents, you cannot subtract unless the base and the exponent are the same. Right here, we have base 10 for both of these values, but we have different exponents. We have 10 to the fourth and 10 to the third. That's not allowed if you're adding or subtracting. You have to have them have the same base and the same exponent. It's just like how you cannot add or subtract x squared with just plain old x. The exponents don't match. You can't add or subtract x to the third with x squared because the exponents don't match. Since the exponents don't match here, we cannot subtract them. But what we can do is change them so the exponents do match, and then we can subtract. So here's how we do that. Take the one that has a larger exponent and leave it as the way it is. So 2 times 10 to the fourth, I'm going to leave it that way. So we'll leave 2 times 10 to the fourth. The one with the smaller exponent, I'm going to make it match the one with the bigger exponent. So I'm going to change the 3 to a 4. So I have 2 times 10 to the fourth. Let's see if I can write this okay. 2 times 10 to the fourth power. And I'm going to subtract, and I'm going to have something times 10 to the fourth power again. But I'm changing this 3 to a 4, which means I'm making this whole number 10 times bigger because I'm adding one more 10 into the exponent. We're multiplying by 10 4 times now rather than just multiplying by 10 3 times like we were before. So like the similar problem, if you make one part of your scientific notation 10 times bigger, you have to make the other part of the scientific notation 10 times smaller. So the 2, which we were multiplying by 10 to the third, needs to be 10 times smaller. And we just do that by moving the decimal point one place over. That's dividing by 10. So 2 turns into 0.2 or 0.2 if you wish. If you want to put a leading 0 in there, you can. But 0.2 now. So again, what we started with was positive 2 times 10 to the third. We're changing that to positive 0.2 times 10 to the fourth. Because 0.2 is 10 times less than 2, and 10 to the fourth is 10 times more than 10 to the third. So one part is 10 times less, but the other part is 10 times more. That way we don't actually change the value of what we're looking at. Now we can subtract these. If you remember your subtraction rules, you keep the base and the exponent the same. So if we have something times 10 to the fourth minus something else times 10 to the fourth, we're going to get an answer that is still times 10 to the fourth. So we have times 10 to the fourth. And now we can do 2 minus 0.2, which is 1.8. So our answer here is 1.8 times 10 to the fourth power. Well, you notice that that is not any of our options. It wants us to say what 1.8 times 10 to the fourth power actually is. Hopefully you've learned that if you have times 10 to the fourth power, that moves the decimal point 4 spaces. So when I do that, I will move it 1 spot to get over the 8, and then I will need 3 more zeros as space fillers. So I will get 1, 8, and then 3 zeros as my answer. So 18,000 kilometers is what I'm looking for, and that is answer D that we see at the bottom there. All right, let's move it right along here. All right, for number 3 here, I'm switching back over to good old pencil and paper since that might work better than my little touch screen here. So let's go ahead and do number 3. Number 3 says a pound of sugar weighs approximately 4.5 times 10 squared grams. If each grain of sugar weighs 6.25 times 10 to the negative fourth of a gram, which is the best estimate for a number of grains of sugar in a 5-pound bag? Now, this seems like a confusing problem, but it's something simple that you've actually been doing since elementary school. It says a pound of sugar weighs this much, each grain of sugar weighs this much. So, how many grains of sugar are in the bag? And then we want a 5-pound bag. So, we multiply by 5 because we start off with just a pound. That's a 1-pound bag. So, first, let's find out how many grains of sugar are in one 1-pound bag. Well, if the whole bag weighs some amount, and each grain of sugar weighs this amount, that's a division problem. Imagine if I said a bag of apples weighed 40 pounds and each apple weighed 2 pounds. That would be a huge apple, but for simplicity's sake, let's say the bag of apples weighed 40 pounds and each apple weighed 2 pounds. How many apples are in the bag? Well, you would do 40 pounds divided by 2 pounds per apple, and you would come up with 20 apples, right? Well, that's what we're going to do here. We're going to say that a pound of sugar weighs that many grams, and each grain, so we've got a bag of sugar, a pound bag of sugar, weighs this much total, and each little grain of sugar in the bag weighs this much total. So that's the division problem. We're going to take this number, 4.5 times 10 squared, and divide it by this number, 6.25 times 10 to the negative fourth. Now I like to write my division problems as fractions, so that's what I'm going to do here. I'm going to go ahead and write 4.5 times 10 squared divided by 6.25 times 10 to the negative fourth. Now we're going to treat this just like any other problem where we're multiplying a number by a base with an exponent and dividing that by some other number multiplied by the same base and a different exponent. For example, we did the lesson where you divide variables, right? Imagine that you had 9n to the fifth divided by 3n squared. You should know how to do this problem. We covered it before. The way you do this problem is you do 9 divided by 3, which is 3. You keep the n, so we'll keep the variable or the base, and then we divide n to the fifth by n squared by simply subtracting the exponents. Here we're multiplying by n 5 times. Here we're multiplying by n 2 times. 2 of the n's on top cancel out with the 2 n's on the bottom, and we're left with 3 n's on top, so n cubed. So 3n cubed. So what's the shortcut? Divide the coefficients, keep the base, and subtract the exponents. Well, that's what we're going to do here. We're going to divide the coefficients, the leading numbers, the 4.5 and the 6.25. We're going to divide those. We're going to keep the base, which is the 10, the times 10, and we're going to subtract the exponents. So here we go. What is 4.5 divided by 6.25? I'll go ahead and get a calculator out. You're totally allowed to use it. So here we go. 4.5 divided by 6.25, and we get 0.72. So I'm going to say equals 0.72. I'm going to keep my times 10 for the base, just like I kept the n in the other problem, just like I kept the n when I did this one. I'm going to keep the base, which in this case is 10. Remember, the base is the thing being raised to an exponent. So in this case, the 10 is being raised to an exponent, so the 10 is the base. So I'll keep the times 10 part, and now I'm going to subtract the exponents. 2 minus negative 4. Well, I'm subtracting a negative, and you should know that when you subtract a negative, you're adding. So 2 minus negative 4 becomes 2 plus 4, which is 6. So I have 0.72 times 10 to the sixth power. Now, this is the right value, but it's not the right answer. And the reason it's not the right answer is because it's not in scientific notation. We should put it in scientific notation by moving the decimal point between the 7 and the 2. You see, 0.72 is less than 1. And if you put something in scientific notation, it has to be greater than or equal to 1 to start with, but less than 10. 0.72 is less than 1, so this would not work. There's also one other part of this problem that we have to remember to do, and that is that we don't care about just a single 1-pound bag. We care about a 5-pound bag. This problem says that a pound of sugar weighs this much, and each grain of sugar weighs that much. So when we divided, we found out how many grains of sugar are in a 1-pound section of sugar, a 1-pound bag of sugar. This whole thing, though, wants the total estimate for a 5-pound bag. So before we put this in scientific notation, we can multiply by 5 in order to figure out what this would be if we have a 5-pound bag. So I'm just going to take our answer, 0.72, I'm going to multiply it by 5. So now the number is 5 times bigger, and we get 3.6, and we still have our times 10 to the sixth. And that is the final answer for the problem, 3.6 times 10 to the sixth. So we got lucky that we had one other step, and when we performed that other step, it put it in scientific notation for us. But if this was our final answer for the problem, then we would have had to move it into scientific notation by moving the decimal point over and making it 7.2. And then since we made that 10 times bigger, we would have had to make the other part 10 times smaller by simplifying 10 to the sixth into 10 to the fifth. So we would have had the answer 7.2 times 10 to the fifth power. That is how many grains of sugar are in a 1-pound bag, and it's written correctly in scientific notation. But then after that, when we multiplied by 5, we would have had 7.2 times 5. We would have gotten 36. So we would have written 36 times 10 to the fifth. And then we would have realized, well, 36 is more than 10. That's not in scientific notation. So then we move the decimal point, the one that's invisible after the 6. We move it over one spot. That's dividing by 10. That's decreasing the 36 by a factor of 10 to make it 3.6. And we make up for that by increasing the times 10 by another factor of 10, and that's increasing the exponent by 1. So either way, we would have still ended up with 3.6 times 10 to the sixth, but just make sure that when you give a final answer, that it's actually written in scientific notation. So we'll go over to our answer. Where's 3.6 times 10 to the sixth? That is answer C. All right, let's do another one. Number 4. Marissa is reading over her blood work results from her doctor. According to the report, there are about 3.7 times 10 to the fifth power platelets and about 9,300 white blood cells in a microliter of blood. What is the total number of platelets and white blood cells in a microliter of blood? So we're looking for a total number. It says, according to the report, there's this much, 3.7 times 10 to the fifth platelets, and about 9,300 white blood cells in a microliter. It wants the total number of platelets and blood cells in a microliter. So we're going to have 3.7 times 10 to the fifth, and we're going to add 9,300. So there's several ways that we can do this. We can go ahead and write out the scientific notation, or we can use the calculator, or we can do a combination of both. Let's start off by doing it by hand the long way. I'm going to start with 3.7 times 10 to the fifth, and I'm going to add 9,300. But there's a problem here. Just like we had a problem before where we were adding numbers, we're not allowed to add two things that have bases with different exponents. The 9,300 here doesn't even have a times 10 part, does it? So we're going to convert the 9,300 into scientific notation, or better yet, into something that says times 10 to the fifth. So how do I do that? Well, if I want to add a times 10 to the fifth in there, that's going to make this a factor of 10 bigger 5 times over. 10 to the fifth is 100,000, so it's going to make it 100,000 times bigger. I need to make this 100,000 times smaller to compensate. If I want to have times 10 to the fifth, I simply just move a decimal point that is right here 5 spaces to the left. So here's what that'll look like. I'm going to rewrite the problem. I start with my 3.7 times 10 to the fifth. Now let's convert 9,300 into something that is times 10 to the fifth. I've got my times 10 to the fifth, and this 9,300, I move the decimal point 5 spaces. 1, 2, 3, 4. Then I'm going to need an extra empty space filler as a 0. So here's what it looks like. Start with 0. Here's my decimal point. And then I have the 0, 9, 3, and then 0, 0. Well, since it's zeros after it, do I really need to write those in? Do I need to put another 0 and another 0 right there? No, you don't need the end zeros. But this is the answer. 0.93 times 10 to the fifth. So this is what we're looking at. If you want to add together two things, one of them that has a times 10 to some exponent, then they both need to have times 10 to that exponent. So now we can add them together. We're going to keep our times 10 to the fifth, and we simply add 3.7 and 0.093, and that's real easy because when we line the decimals up, we just get 3.793. So 3.793 times 10 to the fifth power is the answer. And if we round the 3.793 to the nearest tenth, we have 3.8 times 10 to the fifth. And that is our answer right here. Now, there's a couple other ways to do that. We could have, instead of converting the 9,300 into something that has times 10 to the fifth, we can convert the 3.7 times 10 to the fifth into a regular old number in standard notation. So let's do it that way now. Let's do it again so that we have multiple ways to do this type of problem. What is 3.7 times 10 to the fifth? Simply move your decimal point over 5 spaces. That's multiplying by 10 5 times. So we get 3. Moving it once goes on the other side of the 7, so 7. And then I need 4 more spaces, so I put 4 space filler zeros. So I have 370,000, and then plus my 9,300, so plus 9,300. And when I add those together, I get 379,300. That's my answer. All I have to do now is convert that into a scientific notation. We start with our leading number, which is 3. Put our decimal point between the 3 and the 7, so 0.7. Put the rest of the numbers, 9, 3. And then we have our times 10. And how many spaces would I have to move this decimal point to get it back over here? That's 1, 2, 3, 4, 5 spaces. So we have our 5 again. So 3.793 times 10 to the fifth. And again, when we round that, it ends up being 3.8 times 10 to the fifth. Last but not least, you can just use your calculator if you want to for some of these. If you have 3.7 times 10 to the fifth, you can punch into your calculator 3.7 times 10, exponent button, to the fifth equals, it tells you 370,000. Then you add your 9,300, 9,300, and you get 379,300, which we just got a second ago. But you still need to be able to convert it into exponential form like it's scientific notation. So you still need to know that 3.793 to the times 10 to the fifth power is equal to your 379,300. Okay, let's do another one. Number 5, scientists are examining 2 different strains of a particular bacteria. The length of one strain of the bacteria measures 0.000000438 millimeters. So notice how many zeros there are. There's, if you count them up, 1, 2, 3, 4, 5, 6 zeros, and then 438 millimeters. That's a very small number. While the length of the second strain measures 0.000000726. So that was 7 zeros in that one. How much larger is the first strain than the second? So again, how much larger? Not how many times larger, but how much larger? It's simply a subtraction problem. If you subtract those numbers, you'll get another number that we can put into scientific notation. So you can try to punch them into the calculator. 0.000000438 minus 0.00000 and another 0, 726. And when you do that, you get this. What is this in scientific notation? How many zeros do we have leading? 1, 2, 3, 4, 5, 6 zeros. And then you have your 3. So if I'm going to convert this to scientific notation, I need to move that decimal over in between the 3 and the 6. That's moving it 7 places. So then the result for that would be a 3, a 0.654 times 10 to the negative seventh power. Remember, when you want tiny numbers, you're using negative exponents. So it was 7 spaces, but since I wanted to move this direction in order to make a tiny number, I'm going to have a negative exponents. So 7 spaces, and since it's this tiny little decimal, I put negative 7 as my exponent. And when I look over here, I've got 3.654 times 10 to the negative 7th. Another way you could have done that is to convert them both into something that has times 10 to the same exponent. But if they give you standard notation to start with, then using standard notation that you already know how to use is probably the best way to go ahead and subtract. Then you can just convert your answer to scientific notation afterwards. Okay, let's go ahead and do another problem. Number 6, for a science experiment, Mr. Duncan mixed 0.00055 pounds of sulfur. That was 3 zeros and then a 5. And he mixed with that 0.00104 pounds of iron powder. So this one had 3 zeros before the numbers that we started caring about, our significant numbers, and then this one only had 2 zeros. So we mixed those in an iron powder in a test tube before heating it. What is the total weight of the mixture? Well, if we want the total weight of 2 different things and we know how much each one weighs individually, we just add them together. So let's go ahead and add these. 0.00055 plus 0.00104 equals, and we get 0.00159. When we go ahead and try to convert that into scientific notation, we have to move our decimal point 3 places to get it between the 1 and the 5. So we have 1.59. Since we moved it 3 spaces, we're going to still have times 10, and our number is going to be 3, but again, it's negative because we're talking about a tiny number. This isn't a big old number. This is a tiny amount. When you want to make a tiny amount, we use negative exponents. So we're dividing by 10 3 times. And the way we indicate that we're dividing by 10 is we multiply by 10 to a negative exponent. So 1.59 times 10 to the negative 3rd pounds. Number 7, a set of 4 stars form the shape of a rectangle in space. The length of the rectangle is approximately 4,550,000 miles, while the width of the rectangle is approximately 572 million miles. What is the approximate area of the rectangle? Wow, I'm going to multiply these two together. You know how to find the area of a rectangle. It's width times length. So I'm going to take the length, which is 4,550,000, and I'm going to multiply that by the width, which is 572 million. So we'll go ahead and type those into our calculator. We have 4,550,000 times 572 million. Enter. Oh, geez, that's a really big number. Well, let's convert this giant number into scientific notation. Start with our leading number 2, and then we'll put the decimal. So here we go. We start with 2, and then we put the decimal point, and then we have 6,026, and then after that, it's just nothing but zeros. So I can stop because we got this 0, which we had to write. We had to write that one, but that's because it was between a 6 and a 2. Once you got nothing but zeros left, you don't have to write the rest of the zeros. If we just write all the rest of these zeros in a decimal, it doesn't change anything. So we can stop and we don't have to write those zeros. Always in scientific notation, we put times 10. So how many times do we multiply this number, 2.6026, times 10? How many times do we have to multiply it by 10 to get back up to this number up here? Just count how many spaces you would have to move it to get the decimal from between the 2 and the 6 all the way back down to the end where it should be, the invisible 0 at the end here. Well, we can count by 3s. 3, 6, 9, 12, 15. So this is going to be to the 15th power. And as always, when you calculate area, if you have distance in miles for the width and length, you get square miles as the measurement for your area. So 2.6026 times 10 to the 15th power. By the way, if you want to know how to pronounce this number, there's a system. It's not too hard. You guys know that the first 3 numbers make 1,000. The next ones make million. So if there was a 1 in front of that, it'd be 1 million. The next one after that is billion. So if there was a 1 right here, this would be 1 billion. After billion is trillion. So if there's a 1 right here, this is trillion. And after that is quadrillion. Just like after tri for three, like triangle, you might get quad for four, like quadrilateral. After trillion, which starts with TRI, you get quadrillion, which is QUAD, quadrillion to start with. So this number is 2 quadrillion, 602 trillion, 600 billion. So there's a nice little fact for you. Moving right along now. What's the next one that we are going to deal with? Number 8. Number 8. Recent statistics have reported that the total area of Brazil is about 3 times 10 to the 6th power square miles, while the total area of Japan is about 2 times 10 to the 5th power square miles. Create and solve an equation that can be used to find out how many times larger the area of Brazil is than the area of Japan. Now, that's a really, really important word that you need to make sure you're paying attention to. It doesn't say how much larger. If it says how much larger, we just subtract the bigger number and the smaller one and we get our answer. It doesn't say how much larger. It says how many times larger. If I weigh, let's say I weigh 200 pounds and you weigh 50 pounds. If I said, how much more do I weigh than you? I weigh 150 pounds more than you do. If I weigh 200 and you weigh 50, by the way, that would make me bigger and it would make you smaller. But let's say that there's a little kid that weighs 50 pounds and I'm 200 pounds. How much larger am I than that kid? I'm 150 pounds larger. But how many times larger would I be than that little kid? I would be 4 times larger because 200 pounds divided by 50 pounds is 4. So there's a very big difference between how much larger and how many times larger. How much larger is a subtraction problem. How many times larger is a division problem. So let's go ahead and do this. We're going to take the amount that Brazil is, which is 3 times 10 to the 6th, and we're going to divide, so I'll get the division symbol, by how big Japan is, 2 times 10 to the 5th. And then I'm going to get my answer. So just like when you multiply two numbers in scientific notation, there's a shortcut. I'm going to go ahead and show you that shortcut. What is 3 times 10 to the 6th divided by 2 times 10 to the 5th? Let me go ahead and write it down. I like to write these down always in scientific notation form in fractions when I do division. So here we go. 3 times 10 to the 6th power divided by 2 times 10 to the 5th power. So what is this going to be? Again, we're going to treat this just like if they were variables or something. If we divide the leading numbers, we keep the bases, and we subtract the exponents, just like the earlier problem we did. So we have 3 divided by 2. If you punch 3 divided by 2 into a calculator, I mean, hopefully you know what 3 halves is equal to. 3 halves is equal to 1.5. But 3 divided by 2 gives you 1.5. So the answer here is 1.5. And then we keep our times 10, and then we subtract our exponent. 6 minus 5 is 1. Now I'm not going to write the 1 because we never write the exponent 1. It's always implied. If you do not see an exponent, it's an invisible 1. So there's an invisible 1 right there. It's 1.5 times 10 to the 1st power. Well, wait a minute. That's not one of my options here. I have 1 times 10 to the 5th, and I have the minus sign, I have the plus sign. I have a 60 and a 15. Well, 1.5 times 10, if you multiply 1.5 times 10, it moves the decimal place over one spot, and you get 15. 1.5 times 10 to the 1st power is 15. Let's keep it rolling right along. Number 9, which shows the expression below in simplified form? Okay, so I've got two numbers here and I'm subtracting them. Are you allowed to add or subtract if you have the same base but with different exponents? And the answer is no. You are not allowed to add or subtract if you have different exponents on your bases. So we're going to have to convert these two numbers into two numbers that have the same exponent on the times 10. The base needs to be the same, and the base is the same, 10, but they also have to have the same exponent. Either that or we have to convert them both to standard form, subtract, then convert them back to scientific notation for our answer. You might as well just convert one number to make it match the other, and then we'll be good to go. So the way that I like to do this is I always like to make them match the exponent that is greater. What's greater, -4 or -6? The answer is that -4 is greater. So I'm going to make this other one match the -4. -4 is 100 times greater than -6 when you have them as exponents on scientific notation. 10 to the -4th power is like dividing by 10 4 times. 10 to the -6th power is like dividing by 10 6 times. So I'm going to go ahead and convert the 1.8 times 10 to the -6th into something that is times 10 to the -4th. So here we go. I'm going to go ahead and write down my 8.4 times 10 to the -4th power. And what are we going to subtract? Well, if it's going to be times 10 to the -4th power, what do I have to change the 1.8 into? Since I just increased the exponent on the times 10 by 2, I made the number 100 times bigger. Every time you increase it by 1, you're making it 10 times bigger. So increasing it by 1 makes it 10 times bigger. Increasing it by another 1 makes it another 10 times bigger. And since 10 times 10 is 100, 1.8 times 10 to the -6th is going to be increased by a factor of 100 if you just change it to times 10 to the -4th. In order to keep the value the same, we're going to decrease this number by a factor of 100. And that's really simple. It's just moving the decimal point over 2 spots. Every time you move it over a spot, you're decreasing it by a factor of 10 or increasing it by a factor of 10 if you move it the other way. So here we go. If I have the number, and I'll just kind of write it down here so you can see. If I have 1.8 and I want to make this 100 times smaller, moving the decimal point over one spot makes it 10 times smaller, and then another spot makes it another 10 times smaller, and we put a space filler into that spot. So you have 0.018. Some people like to put a 0 in front, 0.018. Same thing. So here we go, 0.018. So there you go. We started off with 1.8 times 10 to the -6th, and we changed it to 0.018 times 10 to the -4th. These two values are worth the same. These ones, on the times 10 parts, are different by a factor of 100, but these two are different by a factor of 100 as well. So they balance each other out because this one is 100 times smaller than this one, but this is 100 times bigger than this. So they balance each other out. Now, since they have times 10 to the -4th, we can subtract. Whenever you add or subtract something times a base with an exponent, you keep the base in the exponent. So I'm going to keep my times 10 to the -4th. And now I simply do 8.4 minus 0.018. And you can put that in a calculator if you like, but you should be able to do this pretty simply if you just line up all decimals and everything. And you get 8.382. So 8.382 times 10 to the -4th is the answer. All right, moving right along. Number 10, one more to go. Here it is, number 10. The number of managed honeybee colonies in the United States in 1946 was about 5.8 times 10 to the 6th colonies. In 2008, the number of managed honeybee colonies was about 2,270,000 colonies. What is the difference in the number of colonies in the United States from 1946 to 2008? You should know that difference means subtract. If you're looking for the difference in two numbers, you're looking for what you get when you subtract them. So we're starting with 5.8 times 10 to the 6th, and then we have 2,270,000. So one of these is in scientific notation, and one of them isn't. You can convert these however you like. If you are going to make them match before you subtract, then you had better make sure they both have the same exponent and base. So you're going to have to change this 2,270,000 into something that has times 10 to the 6th. And you would have to do that even if it didn't work out that way in perfect scientific notation. The other way to do it is to convert this to standard notation, subtract, and then convert your answer to scientific notation. So let's do it both ways. Let's start by putting them both in what would be similar to scientific notation format by making sure they both have times 10 to the 6th power. So we'll start with 5.8 times 10 to the 6th power since it already has that. And I want to subtract, well, wait a minute, what is this number if I need it to say times 10 to the 6th? If I want it to be times 10 to the 6th, then I need to move the decimal point 6 places in this number and see what I get. So the decimal is at the end here. It's imaginary. It's on this right side of the 0. Move it 6 places. 1, 2, 3, 4, 5, 6. And it becomes between the 2 and the other 2. So we get 2.27. So this is what I'm subtracting. Then I go ahead and subtract. I keep my times 10 to the 6th. Anytime you're subtracting or adding and you have a base and an exponent that match up, you keep that base and exponent. And then you have 5.8 minus 2.27. So go ahead and subtract those, and let's see if I can do this in my head. 3 point, and what is that, 5.3? Something like that. 3.53 times 10 to the 6th. And yeah, that's one of my answers right there, 3.53 times 10 to the 6th. Now, what if you didn't do it in that manner? What if you wanted to put it in standard form? That's fine. What is 5.8 times 10 to the 6th? Well, if I take 5.8 times 10 to the 6th power, I take this decimal and I have to move it 6 places. So here we go. I got the 5. My decimal point would be right here, but I'm going to put the 8. That's one spot. Then I have to put in 5 more zeros as space fillers. So that's one spot. 2, 3, 4, 5, 6. So what did I just do? Let me put my commas in there. 5,800,000. There you go. And I'm going to then subtract the 2,270,000. And I just subtract my numbers. You got your 0, 0, 0 over here. You got your 0. You can do all your borrowing, and you're going to get a 3 and a 5 and a 3. So 3,530,000 as your answer. Now all you have to do is convert that into scientific notation. Go to your leading numbers, a 3, put your decimal point, put in the other significant figures, the 5 and the 3. After that, count how many spaces you'd have to move it to get that decimal point back where it needs to be. It would be 1, 2, 3, 4, 5, 6 spaces. So you get your times 10 to the 6th. And again, that is your answer. All right, so good luck with these. Remember to go through the lesson. There's plenty of examples in the lesson if you are being careful and reading through them. There's example videos. There's more videos than I've got. There's example problems written down and stuff for you to do. So go ahead and look at those for extra resources. And don't forget to reach out if you need help. Good luck and work hard.